On the 14th of October 2014, our Sun let out a great big burp, a coronal mass ejection that swept through the solar system at an incredibly fortuitous angle. Several spacecraft and one intrepid Martian rover detected the solar blast, resulting in an unprecedented experiment that stretched all the way from Venus to outer reaches of the solar system. Like so many other groundbreaking experiments in science, this study came about by accident. Back in 2014, scientists working with ESA's Mars Express were preparing to investigate an incoming comet, but they also happened to record the imprint of a solar event, the Interplanetary Coronal Mass Ejection (ICME) of the 14th of October 2014. Which got them thinking, what if other spacecraft recorded this event, and if so, could this solar blast be tracked as it made its way through the solar system? The answer was a resounding yes. The ensuing collaborative analysis, the details of which now appear in the Journal of Geophysical Research Space Physics, involved measurements taken by no less than 10 probes strewn across the solar system, from ESA's Venus Express and NASA's STEREOA through to the Curiosity rover on Mars, the New Horizons spacecraft, and possibly the Voyager 2 probe. This particular ICME, a giant cloud of highly magnetized solar plasma, was not directed at Earth, but the angle at which it spewed forth sent it into the path of Venus, Mars, Saturn and Pluto, planets around which humans have had an active robotic presence. And ESA animation below visualizes the coronal mass ejection as it traversed the solar system. By pulling the data together, this international team of scientists reconstructed the journey of this rather large ICME, allowing them to study changes in its speed, size, and intensity. Previously, astronomers have used models and maths to estimate the spread of coronal mass ejections, but the data collected by these probes offers direct, on-the-scene evidence. In addition to the spacecraft already mentioned, the ICME was also detected by the ESA's Probe 2, the ESA-NASA SOHO spacecraft, and NASA's Solar Dynamics Observatory. It was monitored by 3 Mars orbiters, ESA's Mars Express, NASA's MAVEN, and Mars Odyssey, and, as mentioned, by NASA's Curiosity. Further out, the ICME was tracked by ESA's Rosetta spacecraft at Comet 67 Churyumov-Gerasimenko, and by the NASA's Cassini mission at Saturn. It was felt in the outer solar system as NASA's New Horizons spacecraft was still en route to Pluto. It may even have been detected by Voyager 2, but at such an extreme distance the blip in V2's data may also have been caused by background solar wind. Looking at the data, the scientists were able to paint a picture of a solar eruption as it propagated through space. Planet positions on the 14th of October 2014. Image Agu. When the Sun first let out this great big belch, the ICME burst forth at a speed of 621 miles per second, 1000 km/s. By the time it got to Mars 3 days later, it had slowed down to 402 miles per second, 647 km/s. Rosetta measured its speed at 342 miles per second, 550 km/s, and by the time it got to Saturn, a full month after the ejection, it was traveling somewhere around 300 miles per second, 475 km/s. The scientists were also able to track the ICME's magnetic field over time. Each probe experienced the initial shock, followed by increases in the magnetic field strength and the speed of solar wind. These effects lasted for days. Sudden decrease in number of galactic cosmic rays detected. Image ESA. Several craft were equipped with radiation monitors, namely Curiosity, Mars Odyssey, Rosetta and Cassini, exposing a well-known effect of ICMEs, a sudden drop in galactic cosmic rays. When an ICME passes, it acts like a protective bubble, temporarily brushing aside the cosmic rays. At Mars, the drop in cosmic rays was measured at 20%, and the effect lasted for 35 hours. When it reached Rosetta, the scientists measured a decrease of 17%, which lasted for 60 hours. At Saturn, the effect was just slightly slow, it lasting for nearly 100 hours. These results show that ICMEs slow down as they spread outwards, encompassing a wider region over the distances covered. This unintended experiment was seriously cool, and it highlights the surprising degree to which human technology has spread out into the solar system. That said, it would probably be better to track space weather by distributing dedicated, interconnected probes throughout the solar system for this very purpose. Perhaps someday. Journal of Geophysical Research Space Physics. More space posts.